Tonight I'll be presenting on dimensionality reduction. Really, I wanted to focus on UMAP, but I'll compare it to the PCA and TSNE because those might be the most common. Apologies if all of this isn't, is already known, but on the seismic data side, it may be interesting. Okay, so why dimensionality reduction? Well, there's this thing called the curse of dimensionality, which more or less outlines that in higher dimensions, things kind of get closer to each other, and the variance between Euclidean distances tends to reduce drastically. And for things that need to be separated, higher dimensions probably isn't going to help you get that separation in a meaningful manner. There's a relationship between the number of bins and how much it scales with the classes that you have. So in a simple example here, if you have a line and you have 3 different classes, you really only have 3 bins, or you could only have 3 bins to look at. When you go to a 2D plane, you have 9 bins, and then you go to a 3D plane and that's 27. So it's like it kind of scales exponentially, so that's not really desired. So that's sort of the case of dimensionality in a nutshell. And usually it's been observed that less dimensions tends to get you, there's a sweet spot where you get optimized performance with less features than you would otherwise have expected. So dimensionality reduction more or less falls into 2 different classes, feature extraction and feature selection. But it's typically utilized, or the underlying thought process is that there's something general about the data that you can extract, or that's the assumption. There's something general about the data that you can extract to represent it with less features. So it's useful for things like feature engineering, for 2D, 3D visualization, and just to improve performance and remove redundancy. So a classic example, I guess, would be if you're trying to describe something that's volumetric, you could utilize length and width, or you could just utilize volume. Feature selection, I'm just mentioning it here, even though feature extraction is really what we'll be talking about today. But as a simple example, in feature selection, you could utilize something like a Sharp score to assess the importance of each feature towards a particular model, and then choose the features that are most important. So like in this example here, you can see that, like LSTAT and RM are by far the most important features. And you could try any particular ML algorithm, if that's what you were trying to do, with just those 2, and see if you get improved performance rather than trying to utilize all 12, let's say. But today we'll be talking about feature extraction, and those come in 2 flavors. Sorry, I forgot to mention. So feature extraction is about finding a mapping, whereas feature selection, as the name implies, is about selecting a subset. So the 2 flavors of feature extraction are the matrix factorization methods and then the neighborhood graph methods. I suppose the quintessential example of a matrix factorization is PCA, where you utilize an eigenvalue, more or less decomposition. TSNE is the major representative for the neighborhood graph, but as I hope you'll see today, UMAP is pretty much does a better job than TSNE in most cases, for most of the use cases, and should be the thing that people consider. But there are many other factorization methods like LDA, width-to-vec. Those all kind of fit into matrix vectorization, and isomap and local linear embeddings, Laplacian eigenmaps, they fall into the neighborhood graph sort of representation that you could utilize for feature extraction. Just a simple mention about PCA, which I suppose most people here would be familiar with. You can represent your data set with all of the features naturally, but if you found a subspace, or in a reduced number of dimensions, and you define a basis in that subspace, you could represent your data with just those basis vectors in the smaller subspace. So like that's more or less an example of the equation there. It's important, I guess, that to remember that it's a subspace, and the eigenvalues of that subspace, or the matrix vectorization, the eigenvalues of that is really what you look for in PCA. Yeah, so that was where there. PCA at a broad sort of general level seeks to maximize variance, or tries to project things in new dimensions where there's a lot of variance. So in the top left diagram there, you could see you have a general cluster of points in 2 dimensions, but in the regular sort of x2 and x1 projection, it kind of looks like a straight line. Let's say a x2 is equal to x1 kind of line. But when you project it onto the principal components, you could see that it looks like an oval. So one dimension can go in the direction of the oval, like lengthwise, I guess, and then another one can go across the width of the oval, and that helps explain most of the variance that you observe in this data set. So your objective with PCA is to find dimensions where variance is explained. In a nutshell, that's kind of what you're aiming for. And you typically get a graph of explained variance depending on how many components you choose to use. And in this case, in an example graph here, you can see that with 2 components, you're already explaining most of the variance, which would be nice from a visualization perspective. TSNE is basically a member of the neighborhood graph methodology. So what TSNE tries to do is every point looks around at its neighbors and builds a conditional probability model of what are the odds of me selecting, let's say, another point as my neighbor. And the objective of TSNE is to minimize the difference between these various distributions in order to figure out who's a neighbor and who isn't. The key parameter of TSNE is perplexity, and that could be thought of as a variable to control how much of the nearest neighbors you want to look at. It's kind of beyond the scope to talk about local and global structure properly, but TSNE really does preserve local structure and not so much global structure, but we'll get to that when we talk about UMAP. It's very useful for, and at one point, I guess, would have been considered the state of the art for dimensionality reduction, especially in a visualization sense, because it does a pretty good job on a lot of data sets, but it's very time consuming. There are some shortcuts that can be utilized, but in comparison to some other algorithms, it does not scale very well. And if you try to do it on, or you try to project onto something that is not or higher than 3 dimensions, it would be, take an exorbitant amount of time. So UMAP could be thought of as just, I guess, a more mathematically solid foundation, or more mathematically solid approach to TSNE, because it's still building a neighborhood graph, but there's a lot of math that, well, I have not yet been able to wrap my head around, but it has to do with Riemann manifolds and projections onto that Riemann manifold, if you assume stuff is uniformly distributed on that manifold. There are a couple of key parameters for UMAP. That basically it utilizes a minimum distance to build the graph in lower dimensions, but before that, it builds a nearest neighbor graph in the higher dimensional space. So it balances more or less, unlike TSNE, it balances local structure versus global structure. And we'll see examples of that on the next couple of slides. Roughly speaking, global structure is about the, I guess, the distance between, or the relative distance between clusters, whereas local structures more or less just like, okay, clusters exist in a sense, roughly speaking. It's not exact. A quick comparison of the methods, because like I said, to go into each and every one of them specifically is probably beyond the scope of this talk. But PCA is fast, it's scalable, it's interpretable. You know what each dimension is telling. Sorry. Did someone have a question? Oh, I heard something just now. So PCA, every new dimension that you get in PCA explains a certain amount of the variance. So you can say that a particular component explains this amount of the variance. So it's interpretable in that respect. But it does not really handle nonlinear relationships very well. It isn't really particularly good for visualizing 2D and 3D, or in 2D or 3D, because unless your data had linear relationships, it wouldn't really be that good. Does it preserve local structure? It does, if it exists. Does it preserve global structure? No. If you do get new data, do you need to retrain or rerun PCA to obtain your components? Yes, but you don't really need to tune many parameters. In comparison, TSNE is not fast, it's not scalable, it's not really interpretable, and its major use has been for visualization. It's just to gain a sense of what your data looks like in lower dimensions, and it's particularly good at that. It's not good for global structure, and you do have to retrain on new data, as well as there is a single hyperparameter that you would need to tune. UMAP, I'll show some examples later, is extremely fast. It's extremely scalable. The dimensions are not really interpretable, but if you did have to get interpretable dimensions, you'd probably try something like a PCA to begin with. It is really meant for nonlinear data. It's great for visualization, preserves both local and global structure. You don't need to retrain because of how the projection works. You don't need to retrain when you get new data, but you do need to tune the parameters to make sure that you're getting something that makes sense. And I'll show a couple examples before moving on to the seismic side of things. So on, I guess, a data set that everybody's familiar with, MNIST digits, we can see PCA shows us that the data, or in 2 dimensions, the data is kind of separable. I mean, you could see different color bands, but they're not particularly clear, except maybe for the zeros, I guess. But you could think of that as like local structure. So PCA is saying that on some level, in 2 dimensions, this data is separable. TSNE, by comparison, does a much better job of demonstrating that, hey, each of these digits, something about them is different. And we could kind of see the clear bands coming out, except for overlap in some areas, that these are distinct digits. And then you go on to UMAP, and not only can we see that they are separate digits, we can more or less see that, like, for example, the number 0 or the number 1 looks vastly different from, or we can interpret it as looking vastly different than some other numbers that might be, closer to each other. So like a 5 and a 7 might be quite similar in a UMAP sense, but they're still distinct clusters, but just further apart. So the major observation here between like TSNE and UMAP is that UMAP adds in the ability to separate these clusters, or the distance between these clusters adds extra information as to how different something is. So that's what global structure is in a sense. So MNIST digits, we can already see here that UMAP is a clear winner. If you were doing anything visualization-wise with this data set, you wouldn't choose anything else other than UMAP. So having come across, well, a simple comparison between PCA, TSNE, and UMAP, for my MSc, MSc thesis, I needed to utilize, well, one of these methods to assess my how my data could be clustered if there was anything there. So from a visualization perspective, I needed to do dimensionality reduction. So I'll just briefly go over how that data is acquired. Well, I guess I should probably start from this diagram here. So essentially, a ship sails, pulls some acoustic devices behind it. Some listen, some emit sound. On top of the part that emits sound, there's a thing called a near-field hydrophone, and all that does is listen to the source of sound that's been emitted to assess its health. You could think of it as, I guess, a doctor with a stethoscope listening to a heart, and it's like, oh, okay, this sounds like a normal heart. So the near-field hydrophone does pretty much the same thing. It monitors what the sound emitters are doing. The ship more or less sails in a straight line or straight-ish line, pulling an array behind it. And each of these individual times that it sends out a pulse of sound into the earth is called a shot point. And a bunch of shot points together build up a survey. But each of these arrays are made up of air guns. An air gun is just a pneumatic device where like a rapid closure of some sound of a cylinder, pushes sound out into the or an air bubble really into the ocean, and that air bubble collapsing emits a P wave or primary wave, and that is a shock wave that is sound of a particular frequency. Different frequencies to what we hear, but it's still sound in a sense. If we look at the bottom right diagram, which is where the I guess the clusterability sense comes in, each of these air guns has a particular volume, and there's a direct relationship, or there are relationships between the volume of this air gun and the various pieces of metadata that you will get from the near-field hydrophone. So essentially, if you want to monitor the health of an air gun, you look at the metadata that's coming from this near-field hydrophone, which is it's a big field. It's stuff that has to be done, otherwise you'll be sending bad signals into the earth, which is undesirable. So I guess anyone familiar with pandas can recognize that data frame there. So there are 13 pieces of metadata usually that are associated with the sort of sinusoidal wave you see at the bottom right. So the sinusoidal wave at the bottom right is what is recorded at the near-field hydrophone. So there's that major pulse, highest amplitude. That's when the air bubble more or less collapses the first time. It emits that sound energy into the earth. And then it expands, contracts, expands, contracts, and hence you have that sort of damped harmonic motion until the energy peters out, and then it repeats again. So each line or each row in this data frame refers to a particular volume at a particular shot point. So in higher dimension, you could think of this as a 13-dimensional data set that's referring to classes of volumes. And the objective, at least in a particular section of my MSc, was trying to answer the question of whether you could utilize just the metadata in a supervised sense to predict volume reliably. It turned out that the answer is yes, but today it's just really about dimensionality reduction. So the first step was really to look at like some pair plots. This is a subset of the attributes. So we can gain a sense already that the data should be separable. In a couple of dimensions, it looks like it's really separable, but they're very clumped together. There's some overlap. The colors, by the way, represent individual airgun volumes. So if you see any of these pairwise plots with 5 distinct colors, that's already a good sign. But you could see that there are some pairwise plots where the data is like completely mixed together and it's almost useless, right? Whereas some other plots are like, oh, you use these 2 dimensions and maybe you can get particularly good performance from a unsupervised algorithm or maybe a supervised algorithm. But how do we go about choosing these, like which pieces of metadata, which attributes do we keep and which ones we don't? You could use feature selection with like SHAP scores, or you could utilize components, or you could project the data onto a set of new dimensions and utilize those dimensions. So in assessing how the data could be projected into those dimensions, that's where I compared PCA to TSNE to UMAP on the metadata for these pieces of seismic near-field data. And these were the results. So in just 2 dimensions, PCA did a somewhat okay job, but we could already observe that with that little cluster of blue inside of the cluster of green, it would be hard to separate, at least in 2 dimensions. It would be hard to separate those 2 classes just utilizing PCA. And the explained variance graph shows that maybe at a minimum, we would need 4 components to explain most, if not all, of the variance involved. So the next thing to look at would be TSNE, right? So TSNE, I'm always amazed at how the displays look with TSNE because there are lots of interesting funny patterns. So perplexity is the variable in TSNE tests, really. And we could see that with a perplexity of 5, so that's roughly speaking like you look at 5 neighbors to assess clusterability, we get something that is a complete mess. It just looks like a circle, at least in 2 dimensions. It just looks like a circle with stuff colored in all over, almost like an artist's palette. With perplexity value of 30, we can already see better separability. But interestingly enough, there's a bit of orange on the yellow. And I thought that was quite interesting because geophysically, those 2 guns are quite similar. So there's something about the clustering process or the dimensionality reduction process that is seeing bits of that data being, similar in nature. But I didn't have the runtime values here, but this is like this took a huge amount of time to generate. TSNE is does not scale very well time-wise. But UMAP, if you remember, there are 2 parameters that you test with UMAP, and even with just one of these parameters in testing, we can already see. Oh, sorry, I should mention TSNE clearly demonstrates that there's local structure in the data when projected into 2 dimensions, because you can see the classes of airgun volume separated quite easily. With UMAP, we can already see that the nearest neighbors, which controls that global structure, we can see that for varying values, especially like with the nearest neighbors of 100, that this data is quite easily separable. If you needed any proof or indication that there was a hidden separability of your data, pretty much any value over 50 already demonstrates that. But again, quite interestingly enough, the yellows and the oranges, there are bits of the orange and yellow that are joined together, which is quite interesting because even in UMAP, it's indicating that there's a relationship between those two air guns, which is true in a geophysical sense as well. And when you extend further to getting the local structure, we can see that if you choose a minimum distance of 1, and that 1 is just a unit in whatever Euclidean space you're in higher dimensions, you can get your groups to be clumped very close together. And as you decrease that unit distance, you can separate your data, but still get an understanding of the local structure. So in the end, I chose a minimum distance of 0.5 here and nearest neighbors of 30 for my further analysis. But UMAP again was super fast, and it was, to me at least, more interpretable because I was able to tie in how the clusters looked to the geophysics side of things. So I know I probably didn't do enough justice to the UMAP process, but in summary, the UMAP was a clear winner in terms of the results. Things were clearly separable, and there are lots of other uses for it. You could utilize the two-dimensional pre-processing step that you have from UMAP as input to your machine learning algorithms, which is not necessarily something that you could do with TSNE. Because that's not what it was meant for. And it's highly repeatable because of how the underlying math works. And it's much better for visualization than PCA. So in a sense, I guess in any modern era, if you're thinking of utilizing TSNE, don't. Try UMAP first and see how that goes. Any questions?
Okay, yeah, I guess I'll start off as usual. Nice presentation, Gregory. You said one of the disadvantages of UMAP was interpretability, right? And I guess in your case, it didn't matter, right? But in other cases, it would. So how do people manage that?
I guess so strictly speaking, I don't think you should interpret UMAP lower dimensions in the same way that you would interpret PCA. That there isn't a one-to-one relationship, as far as I'm aware, between anything like variance or linear characteristics or anything like that. It's just that projection refers to the Riemann manifold. And maybe if you're able to understand how your data looks like or what your data looks like in that Riemann manifold, it might be interpretable, but unfortunately, I can't, or I don't know how to interpret Riemann manifolds off the top of my head. But if someone is able to do that, then they could tie in, I guess, what their data looks like to the dimensions that they see, I think.
Okay, thanks. Yeah, and nothing else from me. Thanks, Gregory.
Sure, Prof.
Good night. I just had a question about that whole Riemann manifold thing. Now, I'm only like a first year undergrad, so I really don't have the maths to understand all this. But I noticed earlier on you said there was like an issue with Euclidean space, and that just had me thinking about like I think Imzimam had done something on hyperbolic geometry, and I was just thinking if in some sense like a hyperbolic geometry could be considered a subset of like a Riemann manifold, and if there are possibly any links there.
So the distance metric you choose to, so I guess if we went in depth into UMAP, which would probably take a long time, because to be honest, a lot of the math is still not even accessible to me, but you can input to UMAP whatever your distance metric is. I mean, if you want to use Euclidean space, you want to use hyperbolic space or whatever your distance metric is, you can just put that in to your as a variable in your UMAP algorithm. it is by no means restricted to Euclidean space. Euclidean space is just typically what people choose to understand more readily. But as in Zimam's presentation some weeks ago, I believe, he showed the benefits of utilizing hyperbolic projections and why you might want to consider that. But UMAP is extremely flexible. It doesn't change the underlying math. You put a distance metric, it goes to Riemann manifold, it builds the topology for itself, and you're on your way.
Thank you.
I can also confirm that hyperbolic space is actually a Riemann manifold. So that's actually a good catch. It is one.
Yeah. Yeah, I wish I understood all of the math. I mean, the inventor of UMAP did a pretty good job in his SciPy presentation in 2018. It's pretty interesting. If you choose to look it up, I mean, he himself was pretty fun about it. He's like, yes, I'm here to talk about UMAP, but I won't mention any of the math. I'll show you a picture of a theorem. I won't prove it at all. Nice thing is that it works. So yeah.
I think with UMAP, I mean, the maths behind it is pretty heavy.
Extremely.
Like I remember glancing at the original paper and you're seeing like category theory being used.
Yeah.
That's not something that comes to mind too much when you think about ML directly. I mean, sometimes you would see like papers talking about generalizing convolutions to Lie groups and stuff like that. Like to actually see category theory proper inside of an ML paper. That was interesting.
Yeah. And an interesting thing about UMAP as well, I think, is as a pre-processing step, it's I mean, there might be some data sets that it works really well on.